No questions? All right, tomorrow, what lab are we doing tomorrow? 5? And 5 is, what's 5 about? One of the things, starting with Chem 1A, then on to 1B, and especially organic and then beyond, the labs are definitely going to get more intense. And that is, like when I was taking organic, we came in, there was no lab discussion. There was a question, an answer, and then the quiz. And the quizzes were hard. The quizzes weren't easy because you had to have the whole thing memorized, basically. And so, at the very least, because on the day of the lab, I asked some people, what's the purpose of today's lab? And a lot of people don't know. And so, what is the purpose of tomorrow's lab? So most of you are going to read it tonight. And so when you read it tonight, you want to prepare your notebook. We're going to do this in one lab period, KClO3. Actually, there's plenty of time because it's a fairly simple experiment. And so, it's fairly simple as far as the procedure goes, but it's more complex as far as the calculations go. And what we're using tomorrow is KClO3 potassium chlorate. And so you probably want to familiarize yourself with KClO3. When you look at KClO3, what do you think? What stands out about KClO3? We talked about this, right? KClO3, metathesis properties. What are the metathesis properties of KClO3? Did we talk about this? KClO3 metathesis? Does anything stand out about potassium chlorate? It's a strong electrolyte. So one, physical properties, it's soluble. Potassium salts are all soluble. What else? Strong electrolyte. Well, I don't know if anything stands out about KClO3 to you, and so that's why I'm asking. Does anything stand out? Does anything as far as metathesis, nothing stands out to me, because when I look at potassium chlorate, I see potassium ions are all soluble, group 1 and ammonium, and then chlorates, acetates, and what? Chlorates, acetates, and are all soluble. Chlorates, acetates, and nitrates are all soluble. Even though, as far as metathesis goes, nitrate salts and chlorate salts are no big deal, but, chlorates and nitrates are a big deal when it comes to other types of chemistry, right? And so when we're thinking about metathesis, acetates are no big deal. Acetates, when you think about acetates, what comes to mind? Acetates, sodium acetate, acetic acid. Acetates are they very reactive? No, they're mild bases, not very reactive. Acetates, though, like acetic acid, can be oxidized. Some people actually eat vinegar. Actually, a lot of people eat vinegar. Do you get calories from vinegar? Or does it just pass right through your system? Are there calories in vinegar or no calories? Well, actually, when you go on to if you go on and or take biology or biochem, there's something called the Krebs cycle, or what do they call it? Other words for it. Basically, it just is the metabolic cycle, and one of the steps in the metabolic cycle is acetic acid, right? And it's actually metabolite, and so vinegar does have calories, but you know, is vinegar a good fuel? You know, would you use vinegar on your fire? I actually asked this a long time ago. Would vinegar make a good fuel for fire? Burning it. Compared to, let's say, ethanol, you know, an alcohol. Does vinegar make a good fire? No, but is it combustible? Sure is. It burns, you know. What about carbon monoxide? Is carbon monoxide a good fuel if you had a choice between carbon monoxide and methane? Good fuel? No. And so what happens is in the body, you know, we take stuff like if you were to consume something like ethanol, you know, and burn it, you get CO2 and water. If we take ethanol and consume it, you know what we get at the end? If you take ethanol and burn it, you get CO2 and water. If you take ethanol and consume it, and so let's say we'll burn this stuff, we get CO2, water, and energy. This is chapter 7. Do you know what a state function is? Have you ever heard the word state function? A state function is something that only depends on the final state and the initial state. It doesn't depend on how you get there. And so the energy involved in this reaction is what we call a state function. It doesn't matter how many steps it takes. Do you think when we combust ethanol, it happens in one step? Have you seen ethanol combust? I'm gonna bring some ethanol in and show you. I still have my bottle. No, actually, when you burn it, it's actually a complex reaction because it gives a nice, beautiful flame. Actually, let's see if I have that here. I'll show you. Well, we'll do this. The one I was looking for is a test jet engine. I don't see it. All right, since this is a state function, we combust it, and we get this much energy. That energy is the change in internal energy between going from the reactants to the products. The states matter because, you know, different states will give us different amounts of energy. In the body, if you consume ethanol here, you know, your body, you inhale O2 and we have redox reactions, but there are going to be many steps here. And so the ethanol, what happens is the ethanol is oxidized to acetic acid, the acetic acid is oxidized to this, which is oxidized to this, which is oxidized to this, and eventually it ends up as CO2 and H2O liquid. And so the beauty of state functions is this: whether we burn it by combustion or we metabolize it, you know, via the metabolic cycles in our body, we get the same amount of energy. And so this is predictable, the amount of energy, because the state functions only depend on the total energy final minus the total energy initial. We have another word for total energy. What do we call it? What do we call the total energy? Well, the total energy is the sum of the kinetic energy plus the potential energy, and the total energy is called I'm sorry? Internal energy is correct. Did you memorize that, or did you look it up? Have you had it memorized? You looked it up? Okay. Do you have to have it memorized? Yes, you do have to have it memorized. Otherwise, you're going to have trouble because we have different forms or different types of energy that we deal with, internal energy being one of them. Okay. Well, this same amount of energy, your body metabolizes it versus combustion, and this is because we're dealing with state functions, and energy is a state function here, at least internal energy is a state function. But anyway, when I think about acetates, acetates are in a whole different category than nitrates and chlorates, but they're in the same category as far as metathesis goes. Potassium chlorate is totally uninteresting for metathesis because nothing's going to happen. I thought we talked about this. Potassium ions, are they acidic, basic, or neutral? Potassium ions. Acidic, basic, or neutral? Did we talk? We didn't talk about this? Take a look back in your notes and see if you have this in the lab. We didn't talk about this? I have a very strange deja vu, but it could be deja vu from years ago. Or maybe people didn't take notes because this was a demo. This was the demo with potassium chlorate and sugar. No? All right, so metathesis, we don't have to really worry too much about this. Potassium, there's no stronger acid, weaker acid, there's no gas formation, there's no precipitate. None of these precipitate out with anything. Acid base, as far as bronzite acid base, nothing, right? No proton donor. Chlorate is a proton acceptor, but chlorate, you know, when you look at its position on the chart, what can you say about chlorate's base strength? What can you say about chlorate's base strength? It's not on this chart, it's on our chart, on the other chart. No, it's not strong. Chlorate is the conjugate base of chloric acid. Chloric acid is a strong acid, therefore its conjugate base is weak, but you know, weak doesn't do it justice. How weak? So weak, we call it, it's so weak we call it neutral. I use the example for chloride. Chloride's the conjugate base of HCl, a strong acid. Chloride, is it very basic? Oh, it's a weak base. If you go around telling people chloride's a weak base, then they're going to think you don't know chemistry very well, because chloride is so weak, it's neutral. Therefore, if you told somebody, oh, chloride's a weak base, so you know we're going to use sodium chloride in our next titration to neutralize our acid because sodium chloride should be a weak base. And then people will think, I don't know what they'll think. I'm sure somebody has thought about that, maybe, I don't know. And so, are you going to use potassium chlorate to neutralize your next unknown acid? No, because what makes a strong acid a strong acid? A strong acid is a strong acid because the anion has no attraction for the proton, or the hydrogen ion. That way they can break apart easily, right? I mean, there is an attraction, but that attraction, the cutoff is, will water disrupt that attraction? If water can disrupt that attraction, then that's the cutoff. And so we say no attraction. And so no acid base, no metathesis, which leaves us with what? Redox. And what do you see about redox for this? What do you see about redox? Yeah, chlorine is quite unhappy, right? Why is chlorine so unhappy? Yes. essentially lost 5 electrons, and so that's not so happy. Well, you saw what happens when chlorine loses 7 electrons. 7 electrons is perchlorate. Perchlorate was some pretty nasty stuff. Did you see that explosion of the perchlorate plant in Nevada? Did I show you that? Huge explosion. The chlorate's bad too, like perchlorate, but not as bad as perchlorate. Why is chlorate not as bad as perchlorate? Yeah, because chlorine plus 7 plus 5 is not as bad, not as electron poor, but still quite electron poor, so chlorate's still. And so what you need to do is you need to create an association. Potassium chlorate, is it dangerous stuff? What do you think? Potassium chlorate, dangerous stuff? What happened when the potassium chlorate and the sugar ignited? Do you guys remember that reaction? Was it pretty violent? Yeah, that was violent. In Chem 1B, in Chem 1B you work with a lot more risky reactions. And one of the reactions is this. I had a student in Chem 1B that poured ethanol into a concentrated solution of potassium permanganate and acid. There are 2 waste jugs in the hood. And I told this student, because they were behind and they were doing a makeup lab, so everybody else was working with potassium permanganate and concentrated acid, some strong oxidizers, because they had to oxidize something that was very resistant to being oxidized. And so I told this person to put their waste in the old waste jug and not in the new waste jug. But, in the rush of doing the experiment, because the person was trying to catch up, they poured the ethanol into the potassium permanganate and acid waste jug. And it wasn't funny because it exploded. And when it exploded, fortunately, it was just a big bang. And the bottle wasn't sealed, so the explosion went out the top of the bottle. And the person was pretty short, and they were inside the hood, and their face got burnt, and their hair got burnt. But fortunately, they were wearing goggles, so nothing happened to their eyes. But after that experience, then I thought, man, people see this type of stuff, and nothing registers, And so this is why I'm making you do chloroform. What can you tell me about chloroform? This is why I'm making you analyze this, because I tell people this, but if they don't figure it out themselves, it never registers. And this is what I learned. I learned that I can say something like 5 times, and then somebody asks me, "Can you repeat it again?" And I'm thinking, why repeat it the 6th time? Because it's not going to register. Probably the best thing is to just try to work it through yourself and understand it. And so this is why things like chloroform, what do you see? Do you see powerful oxidizer? Do you see powerful reducer? What do you see in chloroform? That's what I want you to tell me. And this is why, not everybody, this is why I was asking certain people to tell me, what are the chemical properties of chloroform? This way, when you get a chemical, you think about it. And we do this all the time because we never want to mix. You never want to mix like a strong, powerful oxidizer with a powerful reducer. Now, if this is a powerful reducer and we're mixing it with chlorine, then we have a potential for fire or explosion, right? And so is this good stuff? If this stuff is like methane, then you're making a big mistake mixing it with chlorine, because methane and oxygen is much weaker, well, not that much weaker, but a weaker oxidizer than chlorine. And chlorine's a more powerful oxidizer. Not as bad as fluorine. Fluorine's what I used to work with quite a lot. Did I tell you about the fluorine chemist handshake? Yeah. So, you know, before you mix this with chlorine, you got to think to yourself, is this a powerful reducer? If so, you're making a big mistake, because mixing a powerful reducer with a powerful, and this looks like a great reducer because it looks like a organic. It is an organic, and most organics are flammable. What makes this organic different? Because I'd never mix an organic. This is like, you know, you're not supposed to mix bleach with certain organics, right? Don't do that. And so anyway, this is a part of this, but let's say, you know, this stuff is complicated. If this stuff is complicated, then there are other resources you can go to. And one is, this is what I sent out about the chlorine, is the MSDS. The MSDS are required in every lab. The MSDS stands for Material Safety Data Sheet. And so if we look at potassium chlorate gets a health rating of 3. 4 is the worst health rating. And so 3 is not so great. And fire rating, it gets a 0. Why does this get a 0 fire rating? Did you see that fire we generated in the hood with potassium chlorate? The reason it gets a 0 fire rating is because this is not a combustible. It's not a reducer. This is on the opposite side. This is a oxidizer. The fire rating's extreme here because you can have a nasty fire if you mix this with a reducer. And so somebody who pours ethanol on something like this is just asking for trouble. But in Chem 1B, I've seen it all. And in fact, even in Chem 1A, but much less so. Reactivity is a 0. How can reactivity be a 0? 0 is mild. Well, they must be defining reactivity a different way, right? How are they defining personal protection? J. Well, if you look at the MSDS for water, you know, water is a health hazard too, because, you know, lots of people end up drowning. And so water is known as a toxic as well. And so, you know, when you see so many different toxic chemicals, including water all the way to this, then we have to look into it a little bit deeper. You know, what exactly does it mean to be toxic? You know, for example, you know, people end up drinking chlorine from their home water supply. Although I don't think this area does chlorine. This area, I think, is on ozone. Ozone's better than chlorine because ozone doesn't leave a residue. But ozone can be nasty as well. Ozone is, as you might know, is highly toxic as well. But anyway, here, you know, if there's an emergency, you can always call their 24-hour emergency. All chemical manufacturers are required to list their emergency number here. Some chlorate. The LD50 stands for lethal dose to 50% of the population. This is acute lethal dose, 1,870 milligrams per kilogram. Unfortunately, this is animal testing here. Okay, acute health effects. This is something you want to read, but you know, you have to have some kind of comparison. If you read like sodium chloride, the MSDS there, and compare it to this, you'll see a lot of the same words. You know, but sodium chloride, is it very hazardous? Well, it depends on the amounts. So anyway, this is very hazardous in case of skin contact, eye contact, ingestion. So what you want to do is, you know, before lab, read through the potential acute health effects here, potential chronic health effects here. Chronic health effects would be carcinogenic, you know, mutagenic, tetragenic. Mutagenic, tetragenic is birth defects, developmental toxicity, you're growing. First aid measures. Fire and explosion data. Actually, no data here. Handling and storage. Okay, keep away from combustible materials. Do not ingest, these are just standard handling procedures. This pretty much, when we come down here, this is going to be something that might catch your eye. Extremely reactive or incompatible with reducing agents, combustible materials, organic materials. And so, watch out. All right, so you could read through this. Tomorrow we're using potassium chlorate and MnO2. What's MnO2 called? What's MnO2? MnO2 is called manganese dioxide or manganese 4-oxide. You often see this, that they mix up the rules. According to our rules, we would have called it manganese 4-oxide. But manganese 4-oxide, I know this because most geologists know manganese 4-oxide. Manganese 4-oxide is called desert varnish. Desert varnish is this black coating on rocks out in the desert. It's very hard, unreactive coating. And so you could read through this, avoid contact, if inhaled, remove. Do not breathe dust. Just your standard precautions, avoid contact. That's it. There's some exposure limits for this. And so you'll want to get or familiarize yourself with this. Let's look at some other potassium salt. Let's look at potassium chloride. Potassium chloride occurs in a lot of sea salts. So a lot of people like the taste of potassium chloride. But if you look at the LD50, that's 2,500 milligrams. Potassium chlorate had an LD50 of 1,850 milligrams. So potassium chloride is what we call toxic, too, right? But people eat it all the time. So when you read these things, you have to put it into a wider spectrum. And in fact, you have to narrow it down because to keep themselves safe from liability, all the chemical companies are going to treat every single chemical as being toxic. And this way, if there's anything that ever happens, then they say, well, we warned you, right? But then you have to go back and you have to look, what almost everything that we deal with, including filling up, when you fill up your gas tank with gasoline, you're exposing yourself to carcinogens, mutagens, and tetragens. Things that cause cancer, cause birth defects, and cause defects, genetic defects. And so how do you minimize your risk? Because every day, if you want, what you could do is you could seal yourself up into a room, right? And even in the room, we have volatile organic compounds that are coming off the walls, especially on new buildings. And there's still volatile organics coming off, probably off the paints here, and it's already been years. And so what we have to do is we have to try to minimize these risks because every day we're exposed to these risks. Now, the risk in the lab, because the chlorine has happened before, but in the past it wasn't capped. So I think the reason why this one was much higher concentration of chlorine in the lab than I thought was because it was capped. You know, it's not the first time that somebody's done the potassium permanganate HCl out in the lab. It's like the 15th time that's happened, but it was caught late because of the cap, I think, concentrated it. Normally people detect it right away and then move it into the hood. And so the lab was definitely something I realized you should have handled differently. All right, so this lab and future labs, what I want you to do is I want you to prepare your notebook, and I'm going to check these, and then I want you to put some data for the chemicals that we're using in there. And this data you're just going to copy off the MSDS. And this is pretty much standard practice. People do this, you know, and they just hit the important points of this. You know, for example, reactive towards here, or health hazards there, this type of stuff. Okay, is that clear for tomorrow's lab? Tomorrow, in addition to prepping your lab notebook, I want you to include the, you know, you don't have to include the entire MSDS. What you do is you pick out the important points from the MSDS and include those into your lab notebook prep. Important points for potassium chlorate would be what? You know, that one, it's a health hazard, you know. You could read about the contact, first aid, and two, it's very reactive. You know? Is MnO2 very reactive? You tell me. Either you figure it out, you know, I already told you about MnO2. I hope that the factual data, you know, that geologists call it desert varnish. It's totally unreactive, you know. But it could be unreactive out in the desert, but maybe if mixed with something, it might be reactive. And so you tell me. All right. That we have to finish that lab in one day, and then on Thursday we're starting titration. Are we starting no, we're starting calorimetry experiment. And so calorimetry on Thursday we're going to have some chapter 7 type. Tomorrow's lab is chapter 6. Chapter 6 and some thermo. Talk about the thermo. For example, in tomorrow's lab, what we have to do is we have to heat this up. Let's take a look. KClO3, this is going to be our system. And then there's going to be some MnO2, just a little bit of MnO2 solid. And, you know, is this going to be an object or is this going to be a reaction? And in addition to reactions, we can have processes occur. Okay, what we're interested in is doing this. We're interested in taking KClO3 and MnO2 and going to KCl. Actually, I think I made a mistake earlier with the direction. 3 halves O2 plus MnO2. So in other words, what we're going to do is we're going to heat it up. We're going to heat it up by adding some energy in the form of heat here. If you look at the MnO2, did anything happen to the MnO2? No. All right, what is our system? Is our system a reaction process, or is our system an object? Our system's a reaction process. When we're dealing with an object, the object stays. So if this were an object, we'd have KClO3 and MnO2 here, and we'd have KClO3 and MnO2 there. Nothing changes. The object And so if there's an energy change, let's say the object increased energy, then if it's the same object, then the potential energy, did it change? No, the potential energy stays the same. What changes would have been the temperature. That's the only way, or the kinetic energy. And so here, we're going up like this. Well, this is a reaction process. Reaction processes start off at one temperature. At what temperature do they end at? They end up at the same exact temperature, 25 degrees. Actually, I gotta move a little bit faster because I'm behind schedule a little bit. And so it starts and ends at the same temperature. Now, the first thing we always do is we always look at the system. What is the system? The system is the reaction. The reaction of KClO3, we call this KClO3 decomposition. Is this a redox reaction, metathesis, or an acid-base reaction? This is a redox reaction. And the way you can tell is you just look, you know, did the oxidation states change? They sure did. Oxygen went from -2 to 0 there. And so we have a redox decomposition here. Okay, so our system is the reaction. Our system is just defined as KClO3 solid goes to KCl solid plus O2 gas. To balance it, we'll need 3 halves. Now the MnO2 doesn't change. The MnO2 is what we call a catalyst. And a catalyst is just to speed up the reaction because the decomposition is kind of slow. And so one way we could speed it up is by adding a catalyst. The catalyst is consumed, but it's spit out again. In other words, the catalyst, there's no net change in the catalyst. Yeah. Okay, this is going to cost us energy, so this is an endothermic reaction. So that means, you know, U final is greater than U initial. And what was U called again? U is called the internal energy. Internal energy is the total energy, right? The total energy is the sum total of the kinetic energy and the potential energy. Now, when we look at this, did anything happen to the kinetic energy? Nothing, because 25, 25. And so the change in kinetic energy is 0. That means the only change here is in terms of potential energy. And that's what we see. When we have objects, it's just the opposite. When we're dealing with objects, there's no change in potential energy. The only change is in terms of kinetic energy. Now, when we look at this, we have a system. The system's this reaction. Now, what else do we have to decide? There's one more thing we have to decide when we're defining this. And what is that? See if it's in your notes, because no, it's always going to be a closed system. From now on, we assume it's a closed system, and it might be stated that it's an isolated system, but it will never be an open system. Open systems are too messy to deal with. The only isolated system you're going to have are what we call adiabatic. You'll hear that word, adiabatic, and then you'll know it's an isolated system. Adiabatic in your homework. It's not really discussed in the chapter. We'll look at it. And so there's something called an adiabatic expansion or adiabatic contraction of a gas. Versus the opposite of adiabatic is isothermal. So we're going to deal with an isolated system. I'll tell you the isolated system is called an adiabatic system, and you're only going to deal with it with 2 homework problems, and it's not talked about in the textbook. It's one of those things you have to figure out. Isothermal is usually what we call just a closed system, isothermal. Isothermal just means heat is readily exchanged with the surroundings. Adiabatic means it's cut off from the surroundings. No, it's not that. What is it? Do you have it in your notes? Uh-huh.
Whether the system is either a constant volume or constant pressure.
Yes. That's very important here. Whether it's a constant volume or constant pressure system. If we do this under constant volume conditions, what's going to happen? Well, constant volume is Dalton's, right? And Dalton says that the total pressure is equal to the sum of the partial pressures. It's constant volume. Constant pressure is Avogadro's. Constant pressure says that total volume is the sum of the partial volume. Now, if we do this under constant pressure versus constant volume, it's going, do you know what? It yields different amounts of energy. And so that's why it's so important to keep track of this. Because if this were done at constant volume, we treat it one way. If this is done at constant pressure, we treat it another way. And so let's do this under constant volume. If we did this under constant volume, what do you notice is happening? We're going from a mole of KClO3 solid. You know, well, how much volume does a mole of KClO3 solid occupy? Well, we look at, let's look at its molar mass, potassium chlorate, and its density. Give us an idea. Let's just go to Wikipedia. Its molar mass is 122, and so there's 122 grams. Its density is 1.3. So it's going to be about, per cubic inch, 2.34 per cubic centimeter. And so 122 divided by 2 is going to be about 60. And so a mole of this is going to be about 60 milliliters in volume. So we got 60 mils. The MnO2, we're just adding a tiny spatula scoop, about the size of a match head. And so the volume of a match head is just ignored. And so we're going from 60 milliliters, that's V initial. And so we do this at constant volume. And so we have 60 milliliters here, roughly. And then that means we gotta have roughly 60 milliliters here if we just do it in the container. It depends, we do it in a 500 milliliter container, that's fine, filled with air, you know. Or, let's do this. We're going to put it into a 500 milliliter container. So we got 60 milliliters of solid plus about 490 whatever milliliters of air. 499, oh no, 60 milliliters, yeah. Just say air. And so this air is going to exert a pressure. The pressure of the air, we'll just say it's atmospheric pressure because it's easy. The pressure of the air is 1 atmosphere. So we'll go with a 500 milliliter container. Well, it's constant volume, so the 500 milliliter container is going to stay 500 milliliters. But this is going to decompose. Now KCl, the volume of the solid doesn't change much because KCl has roughly the same density. You know, the density of potassium chlorate is 2.34. What was the density of KCl? Let's take a look. The density of KCl is 1.98. So the volume did change, but not by much. It was, rather than about 60, it's a little less than 60 now. But still about 60. Because both of them have a density of roughly 2 grams per cubic centimeter. And so we go from 60 mils here to about 60 mils here, but there was a big change. What was the big change? We added 1.5 moles of gas. 1.5 moles of gas occupies what volume under normal conditions? Well, a mole of gas occupies what volume under normal conditions? 24.45, or just call it 25. So if a mole of gas is about 25 liters, then 1.5 moles would be about 37.5 liters, 38 liters. So under normal conditions, we should get 38 liters of O2 gas, but this is at constant volume. Being at constant volume, our volume is fixed at 500. And so what we're going to do is we have the air in here. The air, nothing changed about the air. The air is still at 1 atmosphere. But now we just added 1.5 moles of O2. 1.5 moles of O2, and we've got to squeeze it down into a volume of 500 milliliters, which means the pressure is going to be pretty high. Take 38 liters of gas and compress it down to 500 milliliters, and the pressure is going to be very high. And so, in other words, the pressure of the O2 is going to be very high. And so what does Dalton's law say? Dalton's law says that the P total is equal to the sum of the partial pressures, that is the pressure of the air plus the pressure of the O2, which means the pressure is going to shoot way up. Well, I hope the container's strong, because if the container is weak, what's going to happen? It's going to explode. It's going to be a pressure explosion versus a proper chemical detonation. You know, you build up too much pressure, and if the container is not strong enough, the container is going to break and cause the pressure. And so if this were glass, you better be very careful. You know, there's been some, when I was in the lab, there was a glass explosion because the pressure got too high in the container. And it was really weird because about waist height, there was just shards of glass in 360 degrees around, but it was just at waist height. Nothing below, nothing above. And it was just like a perimeter. So the weirdest explosion that I've seen happened there. Well, anyway, the pressure is going to be very high here, and so the container has to be strong. So whenever we work with a constant volume system, we typically use a container that is exceptionally strong, and this container is given a name to it. Do you know what they call a container? This container is usually heavy-walled stainless steel with bolts securing the lid. Just heavy, like grade 8 bolts, or actually grade 5 bolts or something, you know, which are really strong bolts. That way it won't explode. It looks like a submarine kind of thing. Do you know what they call this container? Well, they often use the word calorimeter, but they call it a special kind of calorimeter. They call it a bomb. And so they call this a bomb because they don't want it to be a bomb, basically. And so when we do constant volume, we always use a bomb or bomb-like apparatus, you know, something that can withstand the high pressure, or vacuums. You know, vacuum, if you suck gas away, you know, in a vacuum, it's going to potentially implode rather than explode. And so things that can potentially implode, we also need a bomb apparatus or bomb-style apparatus to prevent implosions. So that's at a constant volume. And so the system volume doesn't change. So we have V final and we have V initial. And V final and V initial, they're equal. The volume didn't change. All right, the other way we could do this reaction is under What type of conditions? The other way we could do this reaction is under constant pressure conditions. So constant pressure conditions, this is maybe more simple because we start off with some potassium chlorate and some MnO2. This is about 60 mils, we said, roughly. And then we're going to do what? Well, actually, we could just do this in a container like this. But the container is special because the container is still a closed system. Oops. So we might have some air here. And this air, you know, the air is going to have some pressure associated with it. What's the pressure? And some volume associated with it. And then when we complete this reaction, what's going to happen? Well, all of a sudden the volume is going to expand greatly. And so now we're going to have some KCl here versus the KClO3. And what's a new volume? Well, what happens is this. At constant pressure, the pressure of the air is 1 atmosphere. I should have done this with the other, but I didn't. What's the pressure of the mix here? The mix is going to be, well, it's going to be the air and the O2. And so the pressure of the mix is equal to pressure of the air, which is equal to the pressure of O2. Everything's constant. But the volume of the mix is going to be different because the volume of the mix will be equal to the volume of air that was originally there, plus now the volume of O2. And so we're going to go from about 60 mils here to about 38 liters here of volume. Now, let's think about this. When you blow up a balloon, this is going to blow up a balloon because if we put a balloon on top of this container, actually this is what I'm doing, I'm putting a balloon on top of this. What's going to happen to the balloon? Well, the balloon's going to expand, right? Hopefully this is going to be a big balloon because 38 liters, right? Otherwise, if it stops, it's going to pop. But anyway, the balloon is going to expand. Could the balloon, well, if the balloon were rigid, it could hold it, but we're going to get a pressure explosion. It's going to pop out. We don't want that. We want it at a constant pressure. So the balloon's got to expand to compensate for all the O2 that's being generated. Now think about this. If you blew up a 38-liter balloon, is that something that's easy? You go, here, can you blow up this balloon for me? It's only 38 liters. If you gave somebody a 38-liter balloon to blow up, are they going to be happy? No, they're going to be unhappy because that's a huge balloon. And that huge balloon is going to take a lot of what to blow up? A lot of time, yes. A lot of what? A lot of energy, yes. And a lot of, what do you say? I don't want to blow up that balloon because that's going to take too much. Too much? What? You would tell them, I don't want to blow up that balloon because that's going to take too much work. It's going to take too much work to blow up that balloon, and I don't want to work that hard. Do you? No. And so what that means is this. There's a big difference between the previous setup. In the previous setup, did anybody have to blow up a balloon? No, nobody blew up a balloon. And you know gases, even though it's under high pressure, gases are mostly empty space. And so gases, you know, if you generate more, they just occupy more of the empty space. You just get more collisions against the wall. And that doesn't require work. What requires work is blowing up that balloon. And so if energy is required to blow up this balloon here to here, right? Then that means this. The amount of heat you have to add is different. If I did this under constant volume, I add a certain amount of heat, right? If I do this under constant pressure, do I add the exact same amount of heat or a different amount of heat? I add a different amount of heat. And the different amount of heat is because of the work that was required to expand that balloon. Even if there's no balloon, the gas still had to expand into the atmosphere. And that expansion is work. And so it's so important, constant pressure, constant volume, because it changes the amount of energy I input into this. And so if I did this under constant pressure, I have to input more energy. I have to input more energy because I got to blow up the balloon. If I do this under constant volume, I don't have to input as much energy. And so heck, you know, tomorrow we should do this under constant volume because that's going to require less heating, right? But we aren't going to do it under constant volume because what do you think is going to happen if we did it under constant volume? We'll probably explode in the lab. Well, how often do we work with bombs? Not that common. Under what conditions do you think we're going to do mostly? Are we going to do constant pressure conditions or constant volume conditions mostly? Like 99% of the reactions you do in lab are going to be under constant pressure conditions. The constant pressure, so you know, maybe we should ignore constant volume. We can't. We can't ignore constant volume. We have to know both constant pressure and constant volume. And so this is one of the things you set out. Each system you analyze, you look for. Is it what? Is it a reaction or a object? And is it under constant pressure or constant volume? We'll just automatically assume that it's closed. It's a closed system. So the next, this is tomorrow's reaction. Tomorrow's reaction is kind of funny because even though, hey, we're doing it under constant pressure conditions, we do two things that's kind of weird. One, initially we assume we assume that the mixture, we're going to generate this. Actually, it's a bit more complicated because in tomorrow's lab, we're bubbling the O2 through water. And what happens when we bubble O2 through water? When we bubble O2 through water, you know what happens? The O2 gets saturated with humidity. And so what we end up with is not pure O2. We end up with is a mixture of O2 and water vapor. And so tomorrow's lab is a little bit different because this mixture of O2 and water, we're going to treat both ways. We're going to treat it in terms of Avogadros because there's air in the system. If there's air in the system, then we add O2 and water, the volume is going to expand, right? And then what we do is we treat it as a constant volume mixture. A constant volume mixture because we want to figure out how much water there is in there. And the only way we can do that easily is by looking at the partial pressures. And so tomorrow's calculation is a little weird because of that. We do both constant volume initially and then flip our frame of mind to constant pressure. Or no, actually we do it opposite. Constant pressure first and then flip to constant volume second. And so it's so easy to use the wrong volume and the wrong pressure. And lots of people do with that calculation. But we won't. So the work, the first law of thermodynamics is this. The first law of thermodynamics says energy is conserved. That is the total energy of the universe. So the internal energy of the universe, final, minus the internal energy of the universe, initial, is equal to what? Well, this is equal to delta U of the universe. What is delta U of the universe? 0. 0. If the energy of the universe never changes, then what are we dealing with? Exothermic, endothermic, etc. What we're dealing with are just exchanges of energy, you know, between the system and the surroundings. But the net energy, there's no change. And so delta U of the universe is equal to delta U of the system plus delta U of the surroundings. And so what we're looking at is we're going to just focus on one or the other. And so typically we just look at delta U of the system. You know, delta U of the system is equal to minus delta U of the surroundings. This minus is just the opposite sign. It doesn't mean it's exothermic. It just means opposite in sign. And so we have something called a sign convention. So for example, let's say the system lost 500 joules. So the system lost 500 joules. That means the surroundings must have gained 500 joules. Because energy, the first law in words in Chem 4 is energy is neither created nor destroyed. Right? Energy is neither created nor destroyed. The total energy of the universe is constant. Those are all ways of saying this. Now, when we look at delta U of the system, delta U of the system is equal to what we call Q of the system plus W of the system. That is, it's the heat gained or lost by the system plus the work done or was done on the system. And so let's take a look at some things as far as sign conventions. When we look at Q of the system, that's heat gained or heat lost. Now, if heat is gained by the system, we say it's a positive value. It's greater than 0. And so we say heat gained by the system. Or if heat was gained by the system, somebody must have lost. Who lost? The surroundings must have lost. And so if Q of the system is greater than 0, that's heat gained. So this is, let's say, plus 500 joules, then somebody must have lost 500 joules, and that must be the surroundings. So Q of the surroundings, which we'll say, is less than 0. In other words, we come up with this. Q of the system is the opposite sign of the surroundings. That is, if this is plus, then this must be minus. If this is minus, this must be plus. Because one gains and the other must lose. If Q of the system is less than 0, then heat was lost by the system. And that means Q of the surroundings must be greater than 0 because the surroundings must have gained heat. And so this is another way of saying the first law of thermodynamics. Another way of saying the first law of thermodynamics is any heat gained or lost must have come from somewhere. Because heat is a transfer of kinetic energy. Heat that is energy is neither created nor destroyed. Let's take a look at the work of the system. The work of the system is the same. When we look at the work of the system, if work of the system is greater than 0, then what that means is energy lost doing work. So the system lost energy doing work. Well, energy is neither created nor destroyed. And so if the system lost energy doing work, then that energy had to go somewhere. Where did that energy go? Although it's kind of weird to think about it, if you spend, let's say you spend 1,000 joules of energy blowing up a balloon, that 1,000 joules of energy doesn't disappear. That 1,000 joules of energy went somewhere. Where did it go? It's kind of, well, it went into the balloon. I had to blow up that balloon, right? And so it just disappeared because I consumed it. But oddly enough, it didn't disappear. It's still, well, where did it go? It went into the, actually, did I get this right? Oh, shoot. Sorry. If energy was lost, it's negative. That means here, this is positive. And so what happens is the surroundings gain energy by or from the system. And if the system gains energy, where did that energy come from? Who lost it? And so energy gained means energy was lost by the surroundings. And so even though this equation doesn't look like it, this says the same thing. Based on the sign convention, this is our first law of thermodynamics. First law of thermodynamics. I'm jumping ahead. I'm jumping ahead because what we're going to do is we're going to look at the first law of thermodynamics just purely from the heat part of this. And we're going to ignore work for right now. And so let's just focus on heat. Heat gained or heat lost by the system. Now when we're looking at the system, we got Q the system here. Now we have two types of systems. One is a object. One is a reaction or process. Now the heat that we're dealing with in terms of an object, we have something called the heat capacity of the specific heat. For an object, Q the system is going to equal the amount times C times delta T. If we're looking at a reaction or process, then we use a different equation because there's no delta T. Reaction or process, delta T is equal to 0 to make our life easier. It doesn't have to be. I mean, we could have a temperature change, but if we have a temperature change, then we have to add two equations and make it a little bit more complicated. It's easy, but delta T equals 0 to make equation easier. And so Q the system, when we're dealing with a reaction or process, is going to equal the amount times what we call delta H. Actually, I'm going to jump ahead. We call it delta H at constant pressure, or we call it delta U at constant volume. Just to give you a little preview. Sometimes delta H and delta U are the same thing. Sometimes they're different. So we'll learn all about delta U and delta H later. Right now we're going to do the simple one. The simple one is looking at objects and some simple reactions. So from the first law of thermodynamics, any heat gained or lost is going to be heat lost or gained by the surroundings. So Q of the system is equal to minus Q of the surroundings. And then we use those equations to figure it out from there. And so let's take a look at a couple of homework problems we're going to do. From the book. Okay, looking at the homework problems, we have some problems with heat capacity and specific heat. Calculate the quantity of heat in kilojoules required to raise the temperature of 9.25 liters of water from 22.0 to 29.40 degrees C. And so we could do some of these just using these equations first and then relating them. And so just using that, we're looking at Q. This is problem 1A. In 1A, we want the amount of heat which is required to raise how much, well, Q, this is an object, it's water. We're heating up some water, so the amount times C times delta T. And so the amount of water we got to figure out, 9.25 liters. And so 9.25 liters, plug in here, times C. C, a lot of people have this memorized for water. To 3 sig figs, it's good over a wide range of temperatures. If we want more sig figs, then we have to narrow it down, because the specific heat of water actually changes depending on what or where you are between 0 and 100 degrees C. And so this is going to be 4.18 joules per gram degree C. And delta T we want is 29.4 is our final. So 29.4 degrees C final minus initial of 22.0 degrees C. So I wonder how many sig figs. Well, first thing is the units don't cancel. So degree C cancels, degree C, but grams and liters don't cancel. And so I'll have to add some more conversion factors here to get it to work out. And so the conversion factors just go from liters to milliliters. And then we know the density of water to 3 sig figs. What's the density of water over a wide range of temperatures to 3 sig figs? If you want it to 4 sig figs, forget it. But to 3 sig figs, all of them round off to 1.00 through the entire temperature range. And so we're safe to 3 sig figs. To 4 sig figs we aren't. But it's going to be 1.00 grams per milliliter. And so liters cancel, milliliters cancel, grams cancel, and that leaves us with joules. And so as far as sig figs go, we got 3 sig figs here, 3 sig figs here. How many sig figs do we have here? 29.4 minus 22 is going to give me 7.4 degrees C. Oops, the degrees C cancel. So that's 2 sig figs there, infinite sig figs here, and 3 sig figs here, which means I'm only going to be allowed 2 sig figs in my final answer. And what does it come out to? What is it? 29,000 joules? Or 29 kilojoules? Is that what other people got? All right, in terms of our system, we want to start visualizing something like this. And so when we visualize something like this, we set up what we call an energy level diagram. Energy level diagram. And so what we're doing is we're starting off at a lower energy, that is a lower temperature water. We have 9.25 liters of H2O liquid, and the temperature is 22.0 degrees C. And then what we're going to do is we're going to add energy here, like this, so that we get 9.25 liters of H2O liquid at 29.4 degrees C. And so we have to add heat, right, to this in order to make the temperature increase. Now you tell me, what is my system? Is my system object or reaction or process? Process, you know what a process is? Not everything is a chemical reaction. You know, when water boils, you start off at water at 100 degrees C, and it's converted to steam at what temperature? When you boil water, the water gets converted from liquid to gas. Does the temperature change? No. And so whenever we have a reaction or process, delta T is always 0 to make life easier. Of course, the steam can get hotter, but we can add that later. Here, the temperature did change. So is our system a reaction process or an object? Our system is an object, 9.25 liters of water. Now, the total energy, U initial, is what? The total energy is equal to the kinetic energy plus the potential energy. And so this is initial, this is initial. The final energy is equal to the kinetic energy plus the potential energy. Was there a change in kinetic energy? Yes. Was there a change in potential energy? No. No, there's no change in potential energy. And here, delta U is equal to Q plus W. When we look at this here, was any work done? Now, when we think about work in chemical reactions is associated with generating gases and consuming gases. And so when we generate a gas or consume a gas, we either have to blow up the balloon or the surroundings blows up the balloon. One or the other. In this case, no work was done, it's just heat. How much heat? And so the work was 0, and this was just equal to delta EK because delta PE is equal to 0. Do you see all these relationships? These types of relationships confuse a lot of people because there are too many things to keep track of for each. And then, you know, people get all mixed up. And when people get mixed up, they get stuck. And when they get stuck, they don't know where to start and what to write down. And so thermo can get complicated, but the problem is we can't ignore all these other things because those, sometimes we need that, sometimes we don't. But anyway, here, where did this heat come from? Well, that means the surroundings must have lost heat because the system gained heat, right? And so the surroundings must have lost 29 kilojoules and the system gained 29 kilojoules. All right, the next one is a bar, aluminum bar, associated with, 33.5 degree C temperature decrease for a 5.85 kilogram aluminum bar. And so this one we can visualize. We have an aluminum bar. It's 5.85 kilograms of aluminum, solid, at some T initial. And then there's some T final here. I don't know what T final is, but I do know what delta T is. And so we have 5.85 kilograms of aluminum solid. Delta T here is equal to 33.5 degrees C temperature decrease. The temperature decrease is minus, this is going to be minus 33.5. T final minus T initial. T initial is bigger, so this is going to come out negative. We have to keep track of the sign. The sign. So, in other words, we're going to, the object cools down. So if the object cools down, Q of the system is equal to the amount times C times delta T. In other words, heat has to be lost, or energy has to be lost in order for us to have this temperature change. How much energy? Well, Q of the system is equal to 5.85 kilograms, and we got to switch this to grams, so that's 1,000 grams per kilogram. And then we need the specific heat. The specific heat of aluminum is a lot smaller than water. It's 0.903 joules per gram degree C. And then our delta T here is minus 33.5 degrees C. And so what does this come out to? What does this come out to? Oh, it's going to come out to a certain number of joules, right, of heat lost. Now, where did that heat go? That heat went into the surroundings. Now, what we can do is we can say, okay, we can say that the surroundings consist of maybe some water. And so if I take this hot piece of aluminum and drop it into water, and there's a 33.5 degrees C temperature drop here, we can figure out, well, you know, how much did the water warm up? Well, how much the water warmed up depends on the amount. So for example, if you took this and dropped it into the ocean, is the ocean going to warm up by much? No, because the amount of water is huge and the amount of heat's not so big. But if we take this and drop it into a bucket of water, then that bucket of water is going to warm up. And so we can figure out how much that warms up based on this. And so we're going to make the calculations a little bit more complicated because we're going to see where that energy goes or where that energy comes from and then see what happened to the surroundings. And so the next series of calculations we're going to look at are what happens to the surroundings. And we're going to limit the surroundings to something simple because surroundings normally is what? The rest of the universe, but that's too much. And so we'll limit the surroundings to something simpler so that we can figure it out. Like a room full of air, we could limit it to that and ignore the heat absorbed by certain things, or a bucket of water, you know, stuff like that.